like a fake cone that you use. So that's what I'm thinking was happening, but total different spray.
Okay, so here is your official second extra credit opportunity for November.
Yeah.
Okay. I know, and everyone should be able to do this. I don't care if you bring me ramen. Okay? Ramen is fine.
Can we actually do
Ramen's
Yeah, people have done it. But you have to bring 5 items. They must be non-perishable. Everybody knows what that means, right? I've literally had to explain that, okay? Because I've had people bring me fruit, yogurt, cheese. I'm like, really? It's not for me, okay? It's going into the food bank, okay? So, honest, I don't go through and pick out my favorite things and take them home.
She's like, oh, I like that yogurt. 5 more points.
Yeah, just don't bring perishable. They go bad if they're not refrigerated. That's what perishable. All right? All right, are you ready?
Oh, no.
No.
Oh, hello.
I have to go back to the piggy bank.
Just to make you happy. If that's possible, I don't know. 2 weeks to Thanksgiving.
And my birthday.
And your birthday?
Birthday's Thanksgiving. Well, it's
Is it that
between
week?
Thanksgiving and Black Friday every year. So this year's Black Friday, last year's Thanksgiving.
Oh,
My niece's is great.
lots of good sales on your birthday.
I know, and then
Shopping
I
spree.
go with my mom, and I'm like, you have to buy this. It's my birthday.
There you go. My daughter, my oldest daughter, her birthday is November 15th.
Yeah, my mom ordered something at the house, and I totally opened it yesterday, and then she got mad.
She really wants a job for her birthday. She's interviewing on the phone again today, and then in person on Wednesday. All right, I got 19. Is that everybody?
For my last 2 birthdays.
22. All right, we're missing somebody. All right, check. Andrew, I want you checking. Good girl. I don't know. I only got 21 and I thought it was 22. Maybe I can't count or add today. Okay, so did you remember or did you figure it out? I really want you to be able to figure it out. Because on the test, it ain't gonna be the same compound. So you need to know how to do it. Okay. Okay, we've been making alkyl halides. Okay, we're gonna do them in 2 types of reactions. The 2 types that they pretty much do, substitution or elimination. So what it means to do substitution means that something is going to be replaced by something else. So in an alkyl halide, it's the halogen that is going to get replaced by something else. Okay, halogen is going to get replaced. All right, in elimination, you actually lose things from the molecule, okay? In this case, we're typically going to lose HX, okay? So here is an alkyl halide, and you will take Y minus, okay? Whatever it is, we're going to use a variety of Y's, we're going to use a variety of X's, but you know there's only 4 X's. Okay, and if you substitute, the Y substitutes for the X, and you get that. We're going to go through how, okay? If you get an elimination reaction, you lose this, okay? And that from the molecule. And notice what we make. What kind of compound is that? An alkene. Alkenes are compounds with carbon-carbon double bonds. Remember all those functional groups? We're going to go through all of them, okay? Okay. Did you write down whatever it was you needed to write down? Okay. I don't know. There was a lot of writing on there. Okay, first we're going to talk about substitution reactions. Substitution reactions typically involve a nucleophile. A nucleophile is something that donates electron pairs to a molecule. We're going to give it electron pairs. So Nu is generic for nucleophile. Okay. So this pair of electrons on that nucleophile will go to the carbon of the CX bond and kick off the halide. Okay, so these electrons come to that carbon and the X minus leaves. Okay, so we call the X minus the leaving group. That says group. All right, notice that we substituted the nucleophile for the halogen. Okay, and thankfully, this reaction that we're going to talk about first only takes one step. The nucleophile comes in, the halide leaves. It's like pushing it out of the molecule. Okay? So far, so good. Okay. All right, so here's a real example. We're going to use hydroxide ion as our nucleophile. And we're going to use methyl iodide as the reactant, the organic molecule. Sometimes that is referred to as a substrate. Substrate tends to get used more in biochem than it does here. But your hydroxide ion has lone pairs on it. Now, when you get hydroxide ion, you will get it as NaOH, KOH, LiOH. There will be a counter ion to go with the OH minus, okay? So you've all seen NaOH, okay? What is the Na plus in this reaction? It is what we call the spectator ion. Do not be hung up with what happens with that. If the reaction is written with NaOH, you need to recognize that hydroxide is the nucleophile. Okay, does that make sense? Okay, so we only are worried about what happens to the organic things. Okay, so the OH minus, one of those lone pairs, there's 3 on there, right? Remember that OH minus, it looks like this. Okay, one of those lone pairs, it wouldn't matter which one you picked, is going to go to the carbon of the methyl group. It is the carbon that the halogen is attached to. And then what happens to the electrons in that bond? They go to the I, so it leaves as I minus. So do you see that it has 4 pairs of electrons on it? So it's an iodide ion. Where do you think the Na plus ends up in the end? Hangs out with the iodide. Okay, it's just the counter ion. This is all the action. Okay, now here's our nucleophile, and this is called the electrophile. The electrophile accepts the electrons that the nucleophile is donating. Okay, here's our product. And notice I minus was our leaving group, okay? This thing in the middle. This whole reaction takes how many steps? 1, okay? So we're going to draw a reaction coordinate diagram, and it's going to have how many mountains? 1. At the top of that mountain is going to be the transition state. The transition state is that little in-betweenness, okay? So when these electrons are going to the C, let me get a a skinnier thing, okay? When these electrons are going to the C, you are forming a bond. And when the iodide is leaving, you are breaking the bond. So this bond is forming, and this bond is breaking. They are occurring together at the same time, okay? So that's why we draw those little dashes. We drew those little dashes before when we were doing overall pictures of resonance boron, okay? It's basically the same kind of thing. It's like in between. Okay, so we're at the top of the hill. We're making an O to C bond, and we're breaking the C to I bond. Okay, when you get enough energy, that will happen and will fall down the other side of the ski slope, right? Some of us roll more than ski. Okay, is that making sense so far? Okay. Okay, what is the nucleophile for the reaction shown below? And then we're going to draw the mechanism. Get 22. A guess is better than no answer. So if nothing else, make a guess. What is the nucleophile? Remember what the nucleophile does. We getting there? Make a choice. Okay. Okay. The nucleophile is what is donating electrons. Who is donating electrons in that reaction? Because there's going to be like hundreds of nucleophiles. So if you look at the reaction, analyze it. Tell me what happened. What happened? How did those two things add together? What happened? Where is this? It left. So it's probably the leaving group. Okay. So what happened here? The O is now attached to this C. Okay. So who is the nucleophile? Who is donating electrons? It's going to be this. What is B? What is B? It's the substrate or the electrophile. It is accepting the electrons. Okay, so how would I draw out the mechanism? You know where you're starting and you know where you're ending, right? Always a good thing to know. I mean, you don't normally get in the car and just start driving, do you? I don't know. You might. Okay. That's going to be the actual nucleophile. What is the Na plus? Spectator ion. Okay. So we've got that plus. That. Now, why am I picking that carbon? Why didn't I pick this one? Because that's the carbon that the halogen is attached to, okay? I mean, it's like, really is logical. Okay, so I'm gonna draw the mechanism. So one of these pairs of electrons is gonna go to this carbon. We can't stop there because that carbon would have how many bonds? 5. So now we're gonna take the electrons in this bond and they're gonna go to the bromine and it's gonna leave the molecule. How do you know that this occurs? Because I told you. How's that? Okay, because the O's, it has to do with base strength. This is a stronger base and Br minus is a weaker base, so it lies on that side. It's not just because of it. Okay, but there's going to be a huge variety of potential nucleophiles and potential alkyl halides. Okay, so you're going to have to be able to recognize that. Okay, so you also get, okay, here's your product that's up there. Whoops. Kind of got crazy there. Okay, I want everybody to see that this right here is the new bond. Okay, that's the blue bond is the new bond. Okay, but what else did I make? What happened with this little thing? We got a bromine and it now has 4 pairs of electrons on it. So it has a what charge? Negative. Are you sure? If you're not sure, calculate it. Seriously. Okay. Well, wait a minute. What about that? Where's that? It's just the counter ion for the halide. Okay. See what we're doing? We're coming in. It's going off. We're coming in. It's going off. That's it. Don't make it harder than it is. It's hard enough. Okay. When we do this reaction, and this one, for this example, we used the first one I showed you, the OH minus plus methyl iodide, okay? The rate was found to be proportional to the concentration of the alkyl halide and the concentration of the nucleophile. Okay, so what order is it? What order is it? It's second order, okay? Come on, I gave you an easy one there. Okay, now how do you know that? Because there's 2 starting materials? No. You know that because somebody did a kinetics study and figured it out, okay? So it's important that you remember that rate laws are based on the kinetics, on how the rate changes as you change the concentration. So if I double the concentration of the alkyl halide, what will happen to my rate? What will happen? What does a rate law mean? It will what? It will double, okay? If I double the concentration of the nucleophile, what will happen to my rate? It will double. What if I double both of them? It'll go up by 4, okay? Is that making sense? What that means, okay? It's dependent on both. So what that tells you about the mechanism from the kinetics is the rate determining step. The rate determining step is the slowest step in the reaction scheme of things, okay? And it tells you who's involved. Now, we only have one step, so obviously that step is the rate determining step. But there's going to be reactions we're going to have more than one step. Okay? Don't worry about those yet. All right. So the rate law tells us which molecules are involved in that rate determining step. Okay? That tells you which hump on your reaction coordinate diagram has to be the highest. Okay? All right, so here is our reaction. We're going to draw the mechanism yet one more time because the more times you do it, the better you get. Okay, so where do I start? I'm going to draw my little arrows. So where do I start? I start at high electron density, just like we did with the residence forms. Okay, remember that a curved arrow means movement of electrons. I probably should have reviewed that already. And I'm using arrows that have 2 sides to the arrow. Remember, you can have arrows like this, or you can have arrows like that. That means 2 electrons. This is 1 electron. When we do free radical reactions, we deal with 1 electron. We're using a whole arrow, so we are dealing with 2 electrons. Do not mix them together. If a reaction is free radical, you stick with 1 electron arrows the whole way. Don't like do a couple and then start doing double, okay? If you're using a double-headed arrow, you use it the whole way. We don't do double-headed and then start doing free radical, okay? They're separate, all right? That actually should simplify your life. Not much, but a little. We'll go with a little. All right, so I'm going to use an arrow with 2 heads. I'm going to start at the OH minus because it is minus, yeah. All right, so I'm going to go from here. Where am I going to go? To that carbon. There's only 1, right? Okay, I can't stop there because if I stopped there and made that bond, that carbon would have how many bonds? 5. Is that allowed? No. So what do we got to do? We got to send those electrons to the iodide and make it leave. Okay, so what's the nucleophile? Do you remember? Whatever is donating electrons. What's the leaving group? Y'all are not saying much today. Thank you, Jessica.
So did you pick that carbon because it's attached to the halogen?
Yes. Yes. So if I had, okay, which carbon do I pick? The one that's on the end because it's closest to the OH minus, the way it's written? No, I pick the one that is this one because it's attached to the halogen. Because there's your polar bond. Okay, there's your polar bond. Okay, what would you get from that one? What would be my product? My organic product. CH3, CH2, CH2, OH. And then you would have lost iodide. It would be the counterion. Sodium or lithium would be its counterion depending on what you used. What your source of OH minus was. Okay? All right, now what is the transition state? That's that in between. So when I draw this arrow, the OC bond is being formed and the CI bond is being broken. So it should be a partial bond. My bad. Okay. You'll notice that the way that I drew it on the other slide, I took those 3 H's and I drew them like this. I probably should talk about that. Okay, so here is an H coming out. Here is an H coming back, and here is an H that is in the plane. Okay, so it's sitting like this. The OH minus is coming here. The iodide is leaving there. Do you see that it's coming in from the back of the molecule? Okay, so this is often referred to as backside attack. Okay.
One more time.
Here's the methyl. It's sitting like this. 1 H is here, 1 H is here, and 1 is down there. So the OH minus is coming in from here, and the iodide is leaving from there. So it's coming in from the back and like pushing it off, like pushing it out of line. Okay? It's called backside attack. I didn't come up with that. Okay, for a transition state, remember that we do this. Okay, this reaction involves a substitution, right? We're substituting one thing for the other. It involves a nucleophile. That's where the capital N comes from. And it has how many molecules present in the rate determining step?
One, as in one.
2.
Oh, 2.
So it's SN2. Both, there's only one step, so that's SN2. Okay? The 2 does not mean how many steps. The 2 means how many molecules are present in the rate determining step. That's important. Okay? So that you don't get them mixed up. Not that that would ever happen. All right, now we're going to draw a reaction coordinate diagram. So you need to have some what? Labels, okay? And on this, the y-axis, we're going to put the energy, and on the x-axis, we're going to put, okay. All right, so what do we start with? We're going to do the reaction we just showed. We're going to start with our starting materials, which are going to be hydroxide ion and methyl iodide. And I'm just going to write them down there, okay? And that's where we are, okay? Then, how many steps was it? So how many mountains? All right, so here we go. Whee! Okay, and if you don't say that, it doesn't work right. Okay, so what's at the bottom down here? I minus. Okay, my minus doesn't look like, I'll circle it. And what else? Oh, I got the iodide. CH3OH, I'm sorry if I'm in the way. Okay. Now you'll notice that I made it what? I put my products lower. Exothermic. Okay. Almost all of them are exothermic, like from a whole year. Okay. So that ought to help you out. All right. So what's at the top? All right. Okay. And you remember how to draw what's on that other slide. Okay. You think you're going to have to draw these by the 4th test? Yes. Okay. This is going to be a reaction of ethyl bromide plus CN minus. CN minus is your nucleophile. And what is your leaving group? This is your nuke right there. Okay. Can you come up with what the product's going to be before I show you the video? And there's a mistake in the video. I'll tell you about it. But all right, so not my bad. I didn't make it. All right, so here is your clue. And then, right, the bromine is going to leave, and what's going to be attached here? What kind of compound is that? The whole thing. It's a nitrile. That's the functional group, is a nitrile. Okay? So how would you get that cyanide ion? You would get it using sodium cyanide or something. Is it poisonous? Yes. So don't be doing that. Okay? Now, I want to show you what this looks like. Okay? That's the cyanide ion. It's that simple. Okay? Notice that this is the side of the cyanide ion. That should be the nucleophilic side. In the video, they messed it up and they made the blue one. Maybe they labeled the carbon as blue. I don't know. Okay, but they use the nitrogen, but it's a good SN2 video, and I can't just find these things. And I don't know how to, whoops, and I don't know how to make them. I have no way of doing that. And I don't know why. Come on. There we go. There's no sound. There it comes. Do you see how it came in from the back? Coming in from the back, and the iodide is leaving from the other side. Do you see how they miscolored the atoms? All right. Just so long as you know that I wanted you to see that. Okay? Now, I want you to notice and look at the two hydrogens on the atom, the carbon atom, that the cyanide's attacking, and tell me what they do. Look at those two hydrogens. Where are they going? They're getting pushed down, aren't they? Okay, that's important. All right, so what we're going to do is hopefully go to the next slide. All right, here are some examples of nucleophiles. Okay, look how many there are on this page. 11, I counted. Okay, notice that iodide is one of them. You can use iodide to replace all of the other halogens. So if you had a chlorine here, you could add sodium iodide and replace the chlorine. Okay, if you had iodide here, you could replace it with OH minus. That's the one we saw. This is the one that we saw in the question, where we had the CH2, CH3 there, okay? Look at this one, SH. Okay, so what happens? It substitutes. Here's one where we have an R group. We're substituting, okay? What about ammonia? Ammonia isn't even negatively charged, but it will function as a nucleophile because it has a lone pair on it. Okay, this makes these little salts. Okay, we won't really worry about them too much this semester, but all right, so here is an azide. Did you ever learn that one in general chem? The azide ion, N3 minus. Sometimes people learn it and sometimes they don't. I always made you learn it because I knew it was going to come up again. Okay, notice that each one of the nitrogens on the azide anion, I guess it's an anion, has a charge. But the overall charge is -1. So you would use something like N3, sodium azide. Okay, would be your source of azide. It doesn't matter which nitrogen you use to start your arrows, except it has to be on the end. Notice we can't use the nitrogen in the middle. Why not? Why doesn't it do that? Because it goes where the negative charges are. Okay, I'll do one like that for an example. All right, then what about this one? Look at that one. That one's carbon, and here is our nitrile, okay, that we saw in the video. On this one uses a triple bond, and that carbon has a lone pair on it. So you can have carbon-based nucleophiles, so you can start making really big molecules. Okay, this one, does that look like an acetate anion? Okay, if you had CH3 there, you could make esters. And here's a weird one, triphenylphosphine. Don't worry about that one too much. I ain't going there. We're going to talk about that a little bit next semester, but it's not a big deal. Okay, so here they were using some of these nucleophiles. Okay, so the bottom one, this is your nucleophile. What's the leaving group? Iodide. The nucleophiles are shaded green. The leaving groups are shaded yellow. Will they be color-coded for you on the test? No. Sorry. You got to pick them out, okay? So how do you pick it out? Look for what's negatively charged. Look for what has a lone pair, okay? That's going to be your nucleophile, and all the halogens are your leaving groups, okay? So notice what we did here. We substituted this halogen for this whole group. So if I make that R a CH3, what is this R going to be over here? A CH3.
Would we ever use fluorine?
Okay, you'll notice that there isn't any examples with fluorine because fluorine is the worst leaving group of the bunch. It doesn't work really good. So pretty much fluorine doesn't get used, which is kind of sad for fluorine, but you know. And in fact, fluorine is so small because of its electronegativity that it is close in size to a hydrogen. And on some pharmaceuticals, what they do is they replace hydrogens with fluorines. They have to do special. But and they put those fluorines in there. It changes enough of the reactivity of something that it can be a drug. It's really kind of interesting. If you ever have to have a PET scan, or any of your relatives have to have a PET scan, when they do a PET scan, they actually take glucose. Remember I showed you those carbohydrates with all those OHs on there. They take glucose and they replace one of those with a radioactive fluorine. Then they put that in the patient's veins and they see where it goes, okay? My husband's had a lot of PET scans since he got sick in 2017, and they wouldn't let me in. I wanted to go in the PET scanner and see it, and they wouldn't let me. But anyway, of course I found out all about what was being done. But they gave him the radioactive glucose that had the fluorine 19s on it. And then he had to sit and do nothing for 30 minutes, okay, to let it get throughout his whole body, okay? Because the cells that are super active are where the glucose goes, because that's where you need the energy from the glucose, okay? You'll learn about that in biochem. Maybe some of them will, maybe. Anyway, so it goes throughout your body, and there is a background because you're not dead, okay, while you have the scan done. You're not dead. So there's a background, and then they put you in the machine to see where it goes. And if you're a cancer cell, you're constantly dividing and growing and doing bad things. And so those cells will grab the glucose. And so they can find them that way, okay? So, but some other places that do take your brain picks up the glucose because it's active, okay? Your eyes, that's a spot. If they have to look for tumors with eyes and stuff, they have to do it different ways because the PET scan, it keeps taking it. So like he was real frustrated. He always gets frustrated doing them because he has to sit there and do nothing for 30 minutes. Like he can't even read a book. He can't look at his iPad. He can't play a game because his eyes have grabbed more of the glucose, okay, than they should be. So he has to just basically sit there with his eyes kind of closed for half an hour.
Not taking a nap.
Well, he can if he goes to sleep, but you know, depends on what time of day you're having it done. Yeah.
Did you get an IV or did they make you drink it?
I think he might have drunk it some.
Because I like I don't know if there's a difference like in the two. Like I know one test you get you drink. Like but I saw you drink iodine, not.
Oh, radioactive iodine? Yeah, I've had to do that too. Yeah, that's kind of gross. Yeah, it's gross. Mm-hmm. But I'm thinking that he drank it, but I'll ask him because they wouldn't let me in. They wouldn't let me in. Okay. All right, so here is a reaction. I want you to come up with the major organic product from that reaction. Oh my God. write out the mechanism again, too. You'll be well versed in this one. It's your first 2 electron transfer mechanism. The first is just a couple.
Taylor, knock it off.
What is he doing?
Oh,
yeah.
yeah. Cracking everything.
Oh, stop cracking.
All the pressure.
All right, are we there? Am I supposed to go to 23? If you're number 23, just make a guess, peeps.
I can't. You don't ever hear people can't.
You can do it. Make a guess. Okay, it's big.
It's not loud. I didn't even see it.
You didn't even see what? Okay, what is wrong with A? What is wrong with C? Just a little bit more. Oh, and this is there. Okay, so what is your nucleophile? So if we were going to write out the mechanism, what would you write? Here's your clue. What? You don't know what to write?
No, we don't know what to do with the NA because it just pieces out.
That's right.
Spectator ion.
It's just the spectator ion.
I know, but I feel like you need
Okay, well, what do you think happens to it?
It's in
ocean,
It hangs out with the,
BR.
yeah, which is your leaving group.
So do we put BR plus NA or is it just BR NA? Chilling. Okay, that's what I thought.
Okay, so you make B plus you make NABR. NABR is your inorganic substance. You'll put it in your set funnel. Well, where will the NABR go? Into your aqueous layer, right? Because it's a salt and it's a sodium salt. They're all soluble in water, right? Remember that little rule back in the dark ages of general chem? Okay, so sodium bromide goes into your water layer. We wash it away. We don't really care. Okay, all we tend to worry about are going to be the organic things. What happens to the organic molecules?
So how do you know, like, I get that Na is like just a spectator ion, but like that's after you tell me, so like how do you know it's just a spectator ion?
Because this bond here between those two atoms is ionic. Okay, so you gotta, if there's a metal ion in there, it's a spectator ion. Okay, it's because you're gonna have that ionic bond, that negative charge, that's your nucleophile. That's where your electrons are gonna start. Okay, all right, so let's look at this. And I'm going to add this sodium acetate is what that's called. Okay. What's the organic product? And write the mechanism. So can you come up with where you're going? And then we'll draw the mechanism. So we're going to have, here's your clue. Don't not put the same number of carbons in that I did. Okay? Don't just put one. Make sure you match me. Okay? Because on that test, it's going to have this plus this gives this, and you've got to write out the products. Okay? So make sure you match what I'm giving you. All right, so now what? What should I write next? What are you thinking? Hmm? What? Okay. Good. What's the inorganic thing for those who are going crazy because it's not balanced? NABR. Okay.
So why is that? Oh, is that? Oh, okay.
Why is what?
You had plus, but that just means like you just meant like and.
This plus this. Yeah. I did. Yes. I didn't mean it was positive.
So would it be NaBr? Is it Br minus?
And Na plus. So they're going to find each other.
Oh.
Okay. With me now? You could write Br minus and you could write Na plus.
Okay. That's
I don't care. All right. So they're inorganic. So how am I going to write the mechanism? There's your clue. How do I know that O is negative? Because the Na plus is attached to it. Okay, so now what do? We go from here to where? Where?
The carbon that's attached to the bromine.
Okay, there. Sometimes it takes a circuitous route. You don't know what those molecules are doing in there. All right, and then what happens?
The bond between the carbon and bromine.
Right, and that occurs in one step. That's it. Don't forget the second arrow. Yeah.
So like if it was wrote just how you wrote sodium acetate over here, what would you like? If what you have drawn in red were your two reactants, like do you have to redraw it like that?
I would, so that you have an O minus. I would redraw it. Yes.
So if you didn't,
If all I asked for was the product, that's all you have to draw. You don't have to write the mechanism all the time. Sometimes I'll ask you for the mechanism, and sometimes I won't.
I guess what I like if there's that bond between the Na and the O, it's an O, right? So
Yeah, but it's ionic. Okay, so you have Na plus and you have O minus. Okay, we don't show movement of electrons for ionic bonds. Okay, don't draw it like this. When we show a pair of electrons, that means that it's a covalent bond in organic chemistry. We're not going to worry about ionic bonds. Okay. All right, how you feel about it? So. All right, at the beginning next time, I'll try to give you like 2 or 3, and you have to come up with the products. Okay, but that won't be till Friday. Okay, so are we doing a review tomorrow?
Yes, good.
At 2?
Sure.
I can't really do it before 2, but I could do it at 2. 2 to 4. I got to leave pretty much close to 4. And then on Thursday is the extra credit. We will also review in class on Wednesday. Thursday is the extra credit speaker. So there'll be a sheet here for you to sign. And it's in here. What is this? It goes to the
Take it today. Could be a good time.